Our next topic is about rate problem. So recall that rate problem uses the formula distance equal to rate times time. And we can express one variable as a function of the other. So let us say time is equal to distance over rate, and rate is equal to distance over time. Problem number 22. A marksman fires a bullet to a target. 3 seconds later, he heard the bullet hits the target. If the speed of the bullet is 800 meters per second and the speed of sound is 300 meters per second, how far is the target? Okay, so in solving rate problem, it is helpful if we will draw a figure. So we have here, so this is the position of the marksman. So he fires the bullet, and the bullet hits the target. And when the bullet hits the target, the sound travels to the marksman. So after 3 seconds, the marksman heard the bullet hits the target. So the question, what is the distance from the marksman to the bullet? Or from the marksman to the target? Okay, so we have the total time of travel, bullet to the target, and then the sound from the target to the marksman. The total time there is 3 seconds. So we can write time of the bullet plus time of the sound is equal to 3 seconds. But we can express the time in terms of distance over the rate. So expressing each time to distance over the rate, then we can have distance over the rate of the bullet plus distance over the rate of the sound. The total time is 3 seconds. Then we can substitute values. Then the only unknown is the t. Problem number 24. Two trains are running in the same direction in two parallel rail tracks. The first train in the front is 150 meters long and running at 120 kilometers per hour. The second train behind the first is 120 meters long and running at 200 kilometers per hour. If the tail end of the first is 750 meters ahead of the front end of the second, find the time required for the second train to completely pass the first train. Okay, so again, a figure is helpful in solving rate problem. So we have here, so let t equal to the time that the second train completely pass the first. And then we will note that we will convert all the dimensions to kilometers, no? Because we have here kilometers per hour, we have here meters. So it is advisable to use one dimension in distance. So I will use kilometers. So the initial positions of the two trains is this. So the first train in front is 150 meters long and running in this direction at 120 kilometers per hour. The second train is 120 meters long and running at 200 kilometers per hour. And the tail end of the first train is 750 meters ahead of the front end of the second. So this is now the position. Okay, so the final position is when the second train completely passes the first train. So we have now the position here. So notice, we have now the first train has traveled this distance, and the second train has traveled this distance, and the second completely passed the first train. So we have here the distances. So the distance traveled by the first, I will just use the front to front distance, no? So this is 120t. So rate times time. So the rate of the first is 120 kilometers per hour, and the time of travel is t. Now notice that the first and the second train, they have the same time of travel, and that is t. So the distance traveled by the second train is 200t. Then we have this distance, no? Okay? So to form the equation, I will use the distance dito. So this distance dito is equal to the sum of the distances here. And that is equal to 0.12 plus 120t plus 0.15 plus 0.75. Okay? So I will write it here. Summation of the distance. Then dito is 200t. Then d1 is 120t. So the only unknown here is the time t. And that is equal to 45.9 seconds. Another variation of rate problem is when the body is moving in water, or let us say affected by water speed or air speed. So the same analysis. So we will just take note that if the body will move in the direction, let us say the airplane will move in the direction of the air, then the resultant speed of the airplane there will be its speed in still air plus the rate of the wind. But if the airplane will move opposite or against the direction of the wind, then the resultant rate of the airplane there will be rate of the airplane in still air minus the rate of the wind. Okay? So to illustrate, we have here problem 23. An airplane flew 660 miles with the wind and took 40 minutes longer for the return flight against this wind. If the plane flies 200 miles per hour in still air, find the speed of the wind. Okay? So the rate of the plane in still air is 200 miles per hour. And then the question is the speed of the wind. Okay? So let x equal to the speed of the wind. So the resultant rate of the wind in going with the wind, so that is equal to 200 plus x. But if the airplane will go against the wind, so the resultant speed there is 200 minus x. So as stated, the airplane traveled 660 miles with the wind and took 40 minutes longer for the return flight. So that means the time of travel for the airplane against the wind is 40 minutes longer than the time for the airplane to travel 660 miles with the wind. So I can write it here. So time against the wind is equal to time with the wind plus 40 minutes. Okay, huh? So the time of the airplane in traveling against the wind is 40 minutes longer than its time in traveling with the wind. But we can express time in terms of distance of a rate, in which the rate here is the resultant rate against the wind and moving with the wind. So time is distance 660 over the rate here. So we have here. So 660 over 200 minus x equal to 660 over 200 plus x plus 40 minutes divided by 60, so that the time is expressed in hours. Then the only unknown here is x. We can solve it, and that is 20 miles per hour. Next problem. A boatman rows downstream in 3/4 the time as it goes upstream. If the velocity of the river's current is 4 kilometers per hour, determine the velocity of the boat in still water. Okay? So this is similar to the previous problem. We have a boat running or moving in water, where in a direction where the boat moves with the direction of the current, the resultant speed is plus the rate of the current. While if the boat will move upstream, opposite of the rate of the current, then the resultant rate is minus 4. Okay? So, we will let R equal to the rate of the boat in still water. So, we have now our equation. So, the boatman rows downstream, so the time downstream is equal to 3/4 of the time in going back upstream. So, time downstream is equal to 3/4 of the time upstream. But time can be replaced by distance over rate. So, I will have here distance over R plus 4 going downstream equal to 3/4 distance over R minus 4 going upstream. The distance D will simply cancel out, and the only unknown is R. So, R is equal to 28 kilometers per hour.